Our project is deep learning-based real-time facial emotion recognition with parallel processing. This is the table of contents of the content we will go throughout our video. I am Razan Al-Umari, and I will introduce our project. Our project is identifying facial expression and classify them into 5 emotions: natural, happy, sad, angry, and surprised. We used image processing to pre-process the data along with deep learning and parallel computing to create the model and achieve higher performance. Additionally, our project is supported by AWS. So our prime goal for this project is to run the parallel code on AWS servers.
My name is Apir, and I'm going to explain the parallel methodology part. In our project, we have utilized 2 main frameworks. These frameworks were TensorFlow and Keras frameworks in order to build our emotion recognition model. And what was our hope is to introduce the parallelism in our code. So we added 2 main operations. These operations were the intra-operation parallelism and the inter-operation parallelism. If we want to differentiate between the 2 operations, in the intra-operation parallelism, it involves parallelizing the execution of a single task by breaking it into a smaller task that could be performed concurrently. Whereas in the inter-operation parallelism, it refers to parallelizing the execution of independent operations. Moving on to the dataset. So the dataset we have used in our project was took from Kaggle website, and it contained over 36,000 of grayscale images of faces. These images were divided into 6 classes. But the actual dataset we have used were contained over 29,000 images. The reason why we have reduced some of the images is because we actually removed 2 classes from the 6 classes we have previously. This helps us to enhance model performance by boosting model accuracy.
Hello everyone, I'm Dan Gurney and I will explain the training code of our project. After import the libraries, you configure parallelism parameter using TensorFlow library that enable you to choose how many threads you wanna run the code on it. Then extract the dataset. As you see here, our dataset have 2 files, one of the trained dataset and another for the test dataset. About the pre-processing, we run all pre-processing steps and for loop to get the average over 5 runtime pre-processing. First, we sharpen the image to enhance the edges of the dataset, and we start the time pre-processing dataset, and we calculate it with millisecond. By image data generator, we apply sharpen image and rescale for both datasets, and as you see here, our dataset have many parameters such as target size, batch size. We initialize it as 32, color mode is a grayscale, also the class mode is categorical. Then we end the time pre-processing dataset and we calculate the average for all the runtime. About our model, we initialize some variables such as initial learning rate, DC step, and DC rate to avoid using garbage value. Our model have many layers such as conventional, max pooling, dropout, and it has fully connected layers. About the compiler of our model, we use Adam as an optimizer function and categorical cross entropy for loss function. As you see here, we create a tensor board callback for training information logging, and also we configure early stopping to stop the training run when the performance not improved. Then last, we train the model with 30 epochs, and as you see here, our code stopped running in 22 epoch, and we reach 87% for training accuracy. And 86% for validation accuracy, and after that, print the training time by milliseconds. Last, we save the model with the two types of files to use it when we run the real-time code that will explain with Fatma. Thank you so much for listening.
My name is Fatma Al-Baik, and now I will present to you the research result analysis. For this step, we adapt the parallel code to run sequentially by configuring the threads to 1, in order to compare and understand how parallel and sequential processing in terms of speed, accuracy, and their impact on the CPU performance. To ensure the accurate result, we turn off the Wi-Fi and shut down all other applications, focusing solely on the task. Let's look at the key findings from our research. CPU utilization. Parallel processing used 100% of the CPU capacity, while the sequential processing used significantly less. Dynamic CPU speed. We observed a higher operating speed in parallel processing at 2.07 GHz compared to 1.62 GHz in sequential processing. Processes and thread management. Despite having similar numbers of processes, parallel processing effectively handled more threads. Execution time in pre-processing and training stages. Parallel processing significantly outperforms sequential processing in execution time, both in pre-processing and training phases. Accuracy in training and validation. Interestingly, the accuracy levels were similar in both methods, emphasizing that the increase in speed does not compromise the quality of results. Loss score in training and validation. Both methods demonstrate comparable loss scores, indicating consistency of performance. This comparison allows us to appreciate the efficiency of resource utilization in both parallel and sequential processing. As you can see here, this is a screenshot of the parallel code during the training time, and on the right corner, the task manager provides us real-time insights into the CPU usage and memory allocation and more. This is a similar screenshot, but this time it is the sequential code during the training time also, alongside with the task manager performance metrics. You can see here the average time it takes for our parallel pre-processing operations, calculated from 5 runs. This slide shows the average time required for the sequential pre-processing, also 5 runs. As you can see in this slide, we will see the time it takes for our parallel code to complete the training for one time, along with the key performance metrics from the last ebook 22, including accuracy and loss score. Finally, this slide mirrors the previous one but focuses on the sequential code. To sum up the result and analysis stage, our research shows the parallel processing is really effective for deep learning tasks because it speeds up a lot. It does require more of the computer CPU power, but the time saved makes it a good choice for a bigger project.
Hello everyone, I'm Azza, and I'll be sharing with you our experiments with Amazon Web Services. So the first step that we started with was to find a suitable server for our problem, which is a deep learning based facial emotion recognition with parallel processing. Since we are going to develop a deep learning model and train it on an Amazon server, we went with choosing the deep learning AMI GPU TensorFlow 2.13 server, which runs on Ubuntu. This type of server allows us to run a deep learning model just like the one that we developed, and it also gives us an access to TensorFlow and Keras, which is the deep learning frameworks that we are using. As you can see here, these are some of the screenshots that I took to show the steps of launching a server. First of all, we choose the AMI from the catalog. So this type of server is running on Ubuntu, and it has a GPU support, and it's also using a TensorFlow framework, which we are using, and it's also have the deep learning libraries already installed, libraries like Keras, PyTorch, and CUDA. Secondly, we are going to choose the instance type. The instance type that we chose is the G4AD X-Large. So this instance type has 4 virtual CPUs. It has the NVIDIA Tesla T4 GPU. It has 16 gigabyte of RAM, and it also have the Amazon Elastic Block Store, which is the storage. So this type of instance is not available for us by default. To install such instance, we had to request a limit increase. So we requested for an increase of the CPUs that we can use. So now I'll be showing the steps of how to request a quota increase. Firstly, we have to choose the service type, which is an EC2 instances. After that, we select the region and the primary instance type. So since we are using G4AD, so the G instance will be the primary instance type. And then we add the new quota value, which is the CPU. After that, we're writing a brief description of the case and submit the request. So Amazon support team responded to us that they received our request, and the following day we received an approval for our request. And as you can see here, in the case history, it shows that the request status is changed to resolved. So that was a simple tutorial of how to request a service quota increase.
Assalamu alaikum. I am Rafa Shemmeri, and I'm going to talk about the most powerful combination between GitHub and AWS. As we know, GitHub is a useful tool for us as a developer, and it helps us to save our work everywhere. Now, I will explain the procedure to link between them, as well as AWS focus on security. Here, we have to share the code between developers, between the team members. Firstly, we have to generate our private key for our instance. I will connect to my instance regularly. Then I will write this command ssh k generation in my to save it in my server. Then I will run the command cat ssh in this to create my public key. And the output I will copy it to save it and paste it on GitHub. Now I will go to GitHub setting and go to SSH and GPG keys. Then I will click on the new SSH key button to link my key with GitHub. Then I will paste the generated public key and link it to GitHub account. Now I will go to AWS and see our instance in EC2. Then I will go to key pairs here. Then I will press action and then click import key pair. I do this process because I want to link between the server and GitHub, because the server has its own key, but for communication you have to generate your own key. Then I will paste the same public key you got from my instance before, and then it is added successfully as it is shown here, emotion synchronization. Then I will go to connect to my terminal and connect to my server again, and I will install Git, and it is a sudo apt install to download Git. Then I will check my connection to for GitHub. Use this command. Then it's showing it's successfully here. You have successfully authenticated. Then I will create my new folder to clone my repository on it. Then I will copy the link from GitHub from the desired repository. Then I will write the command git clone. Then the repository I copy it from there. And now I will do some practical labs with you to show what we have done. As well as we know here, I will go to my AWS console here. Okay, then I will go to my EC2. And go to my instances, because I want to start my server and connect to it. Okay. I change the region to the London, because I create my instance in London region here. Now our project, I will run it here. I will select my needed server, desired server. Then I will click to the action instances. Sorry. Then I will start the instances. Okay, it's successfully started. I will refresh the page until it is 2 out of 2 checked. It is running now, but it's the status check. It is initializing. I will refresh again. And I will copy the public key here and go to Visual Studio Code to run the connection. Here I will start here. This is my Visual Studio. Then here in the corner, I will click the remote window. Here I will go to connect to the host. Here I will configure SSH host. And this is my configuration, my laptop. Okay. Here the configuration, it means you have host. Host is the server name in the AWS. And host name, it is the IP public address. And the user is the platform of the instance or the server used. And identity file, it is the server key, its own key, not the one what we copy or import. Okay. And in each launch, we have to change IP, the public IP address, because it is a change in every instance. The previous one, it is start with 52, and the new one, it is differ. It is start with the 335. Okay, then I will save it and close this window. Again, I will click this button in the corner, connect to the host, and I will launch this emotion recognition server again. Okay.
Hello, my name is Dina Al-Qahtani, and I will talk about our future work. So, although we didn't finalize our project, we aim to enhance our code more and adjust it with Amazon Web Service instance that use more GPUs. But however, we requested some services because AWS has a strict policy about accessing some of these services, which we need. And here are a few of them that provide and support parallel processing, such as SageMaker, and it is fully managed service for building, training, and developing machine learning models, and it provides a wide range of tools and features that make it easy to get started with machine learning, even if you don't have a lot of experience. The second one, which is Lambda, it is a serverless computing service that enables running machine learning model without the need to manage the server. The last one here, S3 is a storage service that provides data availability, scalability, security, and performance, and also it protects any size of data for a specific case, such as backup, archive, and machine learning. And these are the services that we aim to use in our future work. And to conclude, my colleague Rawan will continue.
Assalamu alaikum. Hello everyone, I'm Rawan Al-Harbi. So to conclude this video, our project aimed to improve the precision and the speed of facial expression recognition using parallel computing methods by constructing a sophisticated deep learning model with TensorFlow and Keras. And we successfully accelerated the data manipulation through the integration of parallel data processing techniques. Furthermore, we took the chance to try out AWS servers and services using their powerful computing abilities to improve our computational powers, and how to connect AWS with GitHub. This project has been a valuable learning experience which enhanced our understanding of cloud-based infrastructures. I hope you enjoyed this video. Thank you for watching.